the session.
Hello, thank you. So I'm going to talk about System L, also known as mu bar calculus. And we've had a few talks that mentioned these before. And we've had the kind of logical and philosophical motivation. But for me, I come from functional programming. And the motivation is that functional programming is really good at algebras. We have compositional data types, we have monads, applicatives. And even though there is some work on comonetic effects, coalgebras, I always feel like some things are missing. And so I believe that the classical calculi like mu bar have some of the missing primitives for coalgebras such as par. But this talk is not about that. This talk is about type checking these languages, because I find, even though I want to use them for programming, I do find them a bit unintuitive. And since I like type-driven development, I wanted to build a type checker to just help me experiment things. And in the process of doing that, I found some interesting things of wider interest. So first, because the title of the talk says that it's canonical, so I should qualify what I mean, because it's a very high bar. But essentially, when we do type checking, there's usually a tension between expressivity and how much annotations we need to put in the language. So usually, once you start adding interesting language features and lots of binders, that's when you have to add the more annotations. The nice thing about this approach is that you have a pretty expressive system. You have full polymorphic linear or substructural logic or type theory. There are no choices, so each discipline will be given entirely by its polarity and then what I will call chirality, which I will explain what this means. And the whole thing is structured recursive. There is no unification, no side effects. So what is chirality? So it comes from the Greek word chairo, which means hand. And it talks about a kind of asymmetric duality, whereas like your hands, you have two hands, but they're different. And if you're, as a kid, try to put your left glove on your right hand, you'll remember what I mean. And in our case, the chirality is between producer terms and consumer terms, which is the two main judgments in these classical calculi. And the slogan, which we will unpack, is that the dominant chirality of a term means that the term is checkable, and the sinister chirality is that it's synthesizable, but we'll see what this means. So we've seen a bit about system L, but the idea is that you have three judgments. You have the producer judgments, and these are the same as your normal term as natural deduction, except they have an extra context of outputs. And consumer terms, which have a distinguished input, so they consume this thing, and the bar symbol is the stoop. It's mostly syntactic. And then you have a cut, so which takes a producer and a consumer, and when you're executing, your execution happens by cut elimination. So system L, as you've probably seen before, there are some core rules, which are the mu and the mu bar binders, here called AR and A left. And it's a very minimal system by itself, but this system has a problem, which is it's not confluent. However, you have the same problem in the lambda calculus. If you don't choose a evaluation discipline, then you will also have the same critical pair. So the way you fix this in system L, similarly to lambda calculus, is you use focusing. And there is static focusing and dynamic focusing, where dynamic, you change the operational semantics, and static, you change the type system. And we will look at the static one. So in practice, what this means is that this gives you two subsyntaxes. So the positive fragment, the call by value fragment, it prioritizes data or simple producers. So the main thing is the two introduction rules for plus and the elimination using a case statement, and then the introduction for pairs, and the elimination using the pattern for pairs. And here, in my terminology, you would call it the introduction rules because they're the simple thing. They're the dominant chirality. And the elimination forms, because they're patterns, you would say that's the sinister chirality. And because patterns are hard to type check, you can see where they're the more sinister one. For call by name, you have the dual thing. You have the introduction rules are now copatterns. They're the complicated thing. And the elimination rules are, say, the projections for the products and the par rules for the branching. So similarly here, the dominant chirality is the consumers. They're the primitive eliminations. The sinister one is the copatterns. And you can combine the two. Once you combine the two, okay, now you have two polarities, and you want to go between them with negation. And this is what will allow you to define function types and cofunction types. So the rules for negation, the two negations, one goes from positive to negative, and one from negative to positive. But this creates a problem, which is that now there are certain functions you can't type check anymore. For example, the identity function now takes a positive kind to a negative kind. So in order to fix that, you introduce the shifts. And shifts are kind of like negations, but a little bit different, and I won't explain exactly the difference, except to say that bidirectional type checking also has a notion of shift. And it would be really nice if these two notions of shifts ended up coinciding. And that's foreshadowing. So, okay, that was a brief introduction to SystemL. I hope it wasn't too fast. I assume we've seen some of it. But now the main bit is how do you actually type check it? So the main problem is going under binders. So in the lambda calculus, your main binding form is lambda, which is checkable. And type checking that is easy because you know what the combined type is. So you just take it apart and you put the argument into the context, and then you keep checking. However, for us, we have binding forms, which intuitively you would expect them to be elimination forms, and which means that from our normal intuition with bidirectional type checking, we will expect them to be synthesizable. But this causes a problem, is that how do you, in order to go under a binder, you would have to assume a type, but you don't know what the output type is. So you're stuck. And this is where the sinister nature of the patterns comes out. So the main insight for this, how to fix this, comes from Noam Zeilerberg's reverse bidirectional type checking. So the idea is that instead of starting with a typing context and checking our term against it, we start with an untyped context, and we discover what the types are during the type checking procedure. What this means is that going under binders is easy now because we don't need to know the type we're synthesizing in advance. So this is linear lambda calculus. And what it does is it says at first we're going to synthesize the types A1 and A2 of the pattern. And then we're going to check our expression, the value that it has A1 tends 0, A2. So this is okay. But there is a problem, which is that normally variables are synthesizable. So this means that as you're type checking and you reach the variable leaf, you ask the context. You say, what is the type of this variable? And it gives you the type. On the other hand, in our situation, the context doesn't know the type yet. Our context is pretty barren. So the way the other Noam's insight was that you make variables checkable. So what this means is that as you're going through your term and type checking it, and you get to the variable leaf, and you're checking this variable against some type A, and the variable doesn't know its type. So how do you check it? Well, you just assign the type to the variable. So it's straightforward, but this relies on the assumption of linearity. So this works if the variable is singleton, and you don't use it anywhere else, because otherwise the uses might conflict. So for the purposes of the current talk, I stick to this limitation, but there are ways around it, including using code de Bruijn. So as long as you're very carefully tracking what's happening, you can actually regain copying and deleting. So this is Noam's thing. And the interesting thing here, if you look at this rule of natural reduction again, and you translate this into the sequent calculus, it looks a lot like a cut between a producer of pairs and the consumer of pairs. And in fact, this pattern explains type checking of the entire positive fragment. So essentially, if you have a cut between a producer and a pattern, and the causality goes from right to left, so first you synthesize the type of the pattern, and then you check the producer against this type, and this gives you all of the connectives of the positive fragments. And the causal flow, you could say, flows from right to left, and the sinister patterns to the dominant producers. And this follows our intuition from normal type checking, because we expect bidirectionally that the elimination form is synthesizable and the introduction form is checkable. However, when we look at the dual language, this is flipped on its head. And this, so in the negative fragment, you start with a producer, which is a co-pattern for some co-data, and this is the thing with the binders now. And you cut it with a consumer, which is the simple thing like a projection, which doesn't have any binders and is very easy to check. So you synthesize the type of the co-pattern and check the primitive consumer against it. And so the causal flow is now left to right, from the co-patterns to the consumers. So this gives us the two separate fragments, the positive fragment and negative fragment. And by itself, it's quite nice, but they're not very expressive. So you only get the expressivity once you combine the two into one. So what happens when you do that? Well, first you need to add negations. And this is where things get interesting, because negations, they preserve the dominant chirality. So they invert the information flow. So for example, if you negate a positive value to get a negative value, it's still checkable. And likewise, if you have a positive pattern and you negate it to get a negative pattern, it remains synthesizable. And likewise, if you're going vice versa, so if you're going from negative values to positive values, it's still checkable, just going the other way. And if you turn a co-pattern into a pattern, you're preserving that it's synthesizable. So here we get to the final thing. At the moment, we have had 0 annotations on this type system. So however, where are the annotations? So if you look at the shifts, then a right shift takes a value, which is a checkable thing, to a pattern, negative co-pattern, which is a synthesizable thing. And likewise, it will take a co-pattern to a checkable value. So what does this mean? It means that when we're shifting a value, we're shifting a checkable value into a synthesizable co-pattern. And how we do that is we first synthesize the type of the co-pattern and then check that it's equal to the type of the value we expect. And if we do the inverse and we embed a pattern into a value, well, we do have a problem there because a pattern is synthesizable, and now we're trying to check it. So what does it mean to check it is that we need to add an annotation to it, such that we can check the value we have against the expected type of the co-pattern, and vice versa for the negatives. So essentially, this is the only place where you expect to get annotations. And it matches exactly the shifts from bidirectional type checking, except now we have 2 sets of them. And okay, conclusion, we have a typing algorithm for polymorphic substructural type theory. You can decide the discipline of connective by its principal chirality. Information flow always goes from the sinister pattern to the primitive chirality, and the shifts from system L coincide with the shifts we'd expect in the bidirectional type checking and future work. So the main motivation I mentioned before was effects, and to do that you need a bit more expressivity in your type system. So I'm interested in the type operators for system L, which would mean that the same way that system F omega has a type level lambda calculus, we would expect that the equivalent secant calculus system would have a type level secant calculus, and you would have all these weird continuation types at the type level. I don't know what this would look like, but if there's experts on Mimibar here, would love to talk. The second thing, so the system is substructural, and primarily the motivation for that is, like I said before, we need the variable leaves to be singletons. So I suspect you can generalize that to, as I mentioned before, full nonlinear type system by using code-de-Bruijn. Also dependent types. I think there's a lot of subtleties. So again, if someone's interested to talk, we'll be happy to do so. And then subtyping is a good follow-up because there's currently, as I mentioned, there's no unification. But I think if you did add unification, you could get a bit more expressivity for the type checker, like capturing subtyping. And finally, the categorical semantics of this is very subtle, and some obvious things you'd expect don't actually work. So there's some interesting questions there. And yeah, I think that's my talk.